Well, good afternoon, everyone, and thank you so much for joining us once again for Bite-Sized Corrosion. Last week, Neil reminded us that goedkoop is duurkoop, or you get what you pay for. And I know that that's so real in every aspect of life, and particularly when it comes to materials. Today, Neil's going to be looking at stainless steels and whether they do stain less. Now, since some of my stainless steel cutlery is rusting at the moment, I'm quite interested to see what Neil's going to have to share with us today. So Neil, we're in your hands.
Let's move across to the presentation. In talking about stainless steels, somebody coined the phrase that a stainless steel is so called because it stains less than other materials. And so we're going to unpack that concept a little bit in this short discussion. Before I start, I would really just like to acknowledge these organizations, particularly the South African Stainless Steel Development Association. I have used the data that they provide on their website extensively in putting this presentation together, as well as information from our own in-house in South Africa stainless steel manufacturer, Columbus Stainless, and also the well-known Swedish supplier of stainless steel, Sandvik. Last week, we were talking about material selection, and one of the aspects of materials selection is the selection of materials of construction. And stainless steels are primarily used for the purpose of a material of construction, as opposed to, say, for example, a coating. We saw that stainless steels sit up here towards the top of the galvanic series, meaning that the materials themselves are relatively inactive, they have a high electrochemical potential, and generally they don't corrode to any great extent. In that situation, the discussion was around the galvanic effect that happens when you couple different materials together. Now, we're not really going to talk about that much today, except that to note, stainless steels rely on a passive film. And when that passive film breaks down, the exposed underlying material actually has a potential that is down here somewhere close to mild steel. And that gives us a huge difference in potential between sections of the stainless steel that are passive and those which are not. And this gives rise to some interesting challenges in the actual corrosion of stainless steels. Do stainless steels stain less? Here is a photograph of a stainless steel pump impeller. And that pump impeller is still beautifully shiny, and it certainly has stained less. In other words, it hasn't stained at all. But in the environment in which it was used, it actually suffered from catastrophic erosion corrosion. So although stainless steels may stain less, does not necessarily mean to say that they corrode less at all times. And we're going to have a look today at some of the characteristics of these stainless steels, whereby they perform far better than ordinary constructional steels, carbon steels, provided that they are used in the correct environments. So the stainless steel family is primarily dependent on the alloying of chrome with iron. In order for this family of materials to really work to their best capability, it's necessary that they have a very, very low carbon content. The carbon, if it is present, then reacts preferentially with the chrome that is in the alloy and forms chromium carbides, which can give rise to a number of challenges in terms of corrosion. So one of the best ways of preventing that problem is to make sure that we have very low carbon materials. The amount of chrome that is necessary to impart this corrosion protection is somewhere in the region of 11%. We then add other alloys in order to provide other characteristics. But chromium is the primary corrosion resistant component. If you have a look at this graph, it just shows you that as you get up to the 10, 11, 12% chrome, you start getting absolutely negligible general corrosion rates. The chromium that is added to the steel, to the iron, helps to then form a passive film on the surface. The word passivity means that the material actually does not corrode. It forms an adherent oxide layer, which then prevents further reaction from occurring. And that oxygen comes from the environment, and that film is very topical. Everybody has heard about nanotechnology. Well, that passive film is about 3.5 nanometers thick. That's all. And it provides the skin that then prevents the material from corroding. If you starve a stainless steel of oxygen, you can end up with some unintended consequences. So this passive layer, as we've seen, it's extremely thin, it's uniform, it's continuous, it's stable. In other words, it doesn't change with changing conditions, except in the absence of oxygen. It sticks, so it doesn't come off like mill scale comes off an ordinary carbon steel. The chromium oxide layer on stainless steel sticks. It's smooth. We've all seen how shiny stainless steel can be. It repairs itself. That oxide layer on stainless steel under oxidizing conditions, just like the atmosphere, it recreates that oxide layer virtually instantaneously if it is disturbed. This is not intended to show that stainless steel fails, but when stainless steel does suffer from corrosion failure, it is interesting to note that the predominant cause of that corrosion is not general corrosion. It is what we call localized corrosion. And you can see that there are a number of different types of corrosion that occurs: stress corrosion, cracking, intergranular corrosion, pitting, erosion corrosion, crevice corrosion down the bottom. These are the predominant failure mechanisms for stainless steel, rather than general corrosion, which is the phenomenon that we see with ordinary carbon steels. The metallurgy of stainless steels and its behavior as a corrosion-resisting material is predominantly determined by its microstructure, which in turn is determined by its composition. The corrosion resistance is determined by the composition, how much chrome, how much of the other alloys. Some other aspects of stainless steels, which we are not really going to look at in this discussion, are its mechanical properties. Some materials are hardenable, some are not. Some actually are extremely ductile, which gives them very favorable characteristics. Also, stainless steels have a very poor heat conduction. So you'll often find that stainless steels are used in high temperature application. The first stainless steels were actually produced were what is called Martensitic. The Martensitic structures are structures that are developed when there is carbon around, and these stainless steels were not very stainless in their own right, but they were a lot more corrosion resistant than ordinary carbon steel, and they could be made into hard materials. So for example, your stainless steel knives are Martensitic stainless steels because they can be heat treated to provide high strength, high hardness, and that keen edge that keeps our knives sharp. In order to improve the corrosion resistance, you then look at the ferritic stainless steels, where materials have very low carbon contents, and we'll look at some of the compositions a bit later on. That abbreviation at the end there, BCC, stands for the crystal structure. The BCC stands for body-centered cubic. It is the actual crystal structure of the material itself. Austenitic stainless steels are those which have higher nickel content, and they have a different crystal structure. In this case, it's called face-centered cubic. The difference between body-centered cubic and face-centered cubic is in its geometry. And you find that when these materials change from the one phase to the other, say from austenitic to ferritic or vice versa, they undergo a volume change. And that is why some materials are able to be hardened and others not, because of this particular phase transformation. We have what are known as the duplex stainless steels, where the crystal structure is a mixture of ferrite and austenite, and we'll see why just now. We spoke earlier about the primary role of chromium. If we look at the other materials that are added to the stainless steel, molybdenum and nitrogen will improve the quality of that passive film that is formed. Nickel favors the retention of the austenite phase, which gives us the more commonly known stainless steels, which have excellent ductility and their other favorable mechanical properties. If we have a look at the families of stainless steels, they can sound bewildering, but actually they're not that difficult. You either have the chromium-based materials, where it's purely chrome that has been added as an alloying element, or you have stainless steels which are a combination of chromium and nickel. So to look at the chromium side, we started out with those Martensitic materials, which were the early stainless steels. Superferritics are stainless steels with a very high chromium content. The ferritic and 3Cr12 materials have decreasing levels of chromium. If you go across to the other side, you start off with the nickel-containing materials that are austenitic. You then increase the alloying elements there, predominantly nickel, and you get better heat-resistant materials going through those heat-resistant and the super austenitic materials, very, very high alloy contents. And then in the middle, you've got the mixture of the two, where you've got these duplex materials that have a mixture of ferritic and austenitic microstructures. And we'll see why that is of such benefit. The various grades of stainless steel are characterized by numbers. So you get the 200 series, the 300 series, the 400 series, the 600 series, and so on. The most common series that we find in everyday use in the industrial sphere are probably the 300 series, which are the austenite-based materials, a mixture of chromium and nickel. We commonly call them the 18-8 stainless steels. So the common grades, 304, 304L, 321. 304 is just a basic 18% chrome, 8% nickel. 304L is one with a very low carbon content. And 321 is a material where instead of having low carbon, you add titanium to the material that actually captures the carbon and prevents it from reacting with the chrome. The 316 is the next step up in terms of corrosion resistance, and it has additional molybdenum, which improves the resistance to pitting corrosion. These austenitic stainless steels do have some limitations. In the high temperature range, we're limited to 900 degrees C, 925, okay. And if you need to go higher than that, then you've got to go to more specialized alloys. If you don't have oxidizing conditions, you find that these stainless steels do not perform so well. If you're faced with reducing acids, these acids will break down that passive film, and as a result, these acids are only used at low concentrations and low temperatures. The biggest bugbear of all with the austenitic materials is pitting, crevice corrosion, and stress corrosion cracking. And the common denominator in all of these is the chloride ion. If you have environments that are high in chlorides, then we land up with this phenomenon known as stress corrosion cracking. And also then you can get pitting and crevice corrosion under non-stressed conditions. Stress corrosion cracking happens when you have both stress and corrosion, and generally at higher temperatures. A rule of thumb for stress corrosion cracking of these materials, and that's the 50-50 rule. If you've got 50 parts per million chloride and 50 degrees C, you're likely to get stress cracking. If we deprive the materials of oxygen, then we really have a problem. And this is of in particular importance if you use, for example, stainless steel for a buried pipeline. You are going to reduce the available oxygen. And we find that stainless steel underground does not perform particularly better than ordinary carbon steel and actually needs supplementary protection like coatings or cathodic protection. So the ferritic stainless steels then are fairly straightforward. They are used for sinks and pots and pans and things like that. The advantage of these ferritic stainless steels is that they are not susceptible to chloride stress cracking. Typical materials that you may come across: 409, 430, 3CR12, a South African development that has been very successful. The Martensitic stainless steels, that's your cutlery, where we can use the presence of the carbon to give us the high strength and hardness. These cannot be welded. 410, 420, 431, 440, these are numbers that you will come across with regard to these steels. We saw that ferritic steels don't suffer from stress cracking, but they have poor weldability. Austenitic materials suffer from stress cracking, but have excellent weldability. So now take a duplex stainless. This is a combination of ferrite and austenite, and although they're a little bit more difficult to weld than the austenitic materials, they are now resistant to the chloride stress cracking problem, and they have the weldability characteristics that are closer to the ferritic steels. One of the more common materials that you may have heard about is one of the proprietary alloys, I think it's from Sandvik, SAF 2205, 22% chrome, 5% nickel, and this gives us the duplex metallurgical structure. There's a special grade of stainless steels known as precipitation hardening steels. This is a really fancy metallurgical phenomenon, and it gives us materials that have the characteristics of austenitic materials and very high strength. And it is obtained by having alloying elements that produce fine particles or fine crystallites in the metal, which give us the additional hardness. They're used in very specialized industries such as aerospace, defense, subsea finishing of oil wells and gas wells, and you may come across a material such as this 17-4 pH. All these numbers, I'm sure, will leave you very confused, and that is why you need to go and refer to the publications from the suppliers in order to make sure that you are dealing with the right thing. A general characteristic of all stainless steels is how corrosion resistant are they? And one of the parameters that's been developed is known as the pitting resistance equivalent. And it is given as a number which is based on the chrome, moly, and nitrogen content of the material. If we have a look at these various materials that we've been talking about, you can see that as you go up the alloy tree, you get higher and higher pitting resistance equivalent numbers, which means that these effectively are materials that are more and more and more resistant to corrosion. Right down at the bottom, you can see there the number C276, which with a significantly greater pitting resistance number. This actually goes beyond the realm of stainless steels and is one of the Hastelloy materials, which is more of a nickel alloy than a stainless steel per se. So what are these materials that go beyond stainless steels? In no particular order of preference, you get materials such as alloy 825, the Carpenter alloys, Hastelloy materials like I've just mentioned, and these materials have extremely high corrosion resistance. When we were talking about material selection last week, we mentioned that one has to design not only for operating conditions, but for upset conditions. And we looked at things like temperature, pressure, stress, and environment, and so on, as causing upset conditions. Interestingly enough, one of the upset considerations that I've come across on a couple of instances is that of electrical interference in the process industry. Here is a piece of pipe from a very fancy, very expensive valve made out of Hastelloy C276. And as you can see, it has significant internal corrosion. This piece of plant was designed and developed to handle hot sugar solutions with very high hydrochloric acid content as well. On paper, everything looked fine, and yet this component failed. The operators then attempted to address the issue by lining this very expensive material with another very expensive material in the form of Teflon. And the problem was that the Teflon lining was not fully continuous, and they got even faster failure. And when we investigated this situation, we found that there was a variable speed drive pump in the system which had not been properly earthed. And there was an AC current interference component that was going to earth through the piping. And it was sufficient to break down the passive layer of this very expensive material and cause it to corrode quite drastically. We've also seen similar situations with these very high alloy materials in things like electrolytic chlorinators, where systems have not been properly earthed, and you get stray currents flowing through process plants, which can cause this sort of corrosion. So to come back to our original question, do stainless steels stain less? I think we need to ask ourselves that, is this the right question to ask? Here's a photograph that we saw last week of a stainless steel, which is certainly stained, but actually that's all that's happened. And it's a visual thing. It hasn't actually caused any significant corrosion. The better question is to say, do stainless steels corrode less? Do they corrode less than carbon steels, for example, or other materials? Well, the short answer is yes. But the caveat to that is that they only corrode less if they are correctly utilized and their limitations are kept in mind. And when you do that, then you land up with a very successful corrosion-resistant situation. And this photograph is of a submerged component in a highly corrosive water system, which has been in service in excess of 20 years and is still as good as new. And with that, I will hand you back to Vanessa.
Thank you, Neil. I've always found the stainless tree completely challenging, and that really did help me to come to terms with it a little better. I've got a couple of questions that have come in. First, with 304, for example, 304L, what does the L stand for?
Oh, that's very easy. 304L is a low carbon version of 304. And the point about that is that if you have 304L, it can be welded without too much concern about the formation of these chromium carbides that land up what is called sensitizing the material and causing corrosion in, say, the weld heat effective zone.
And I presume the same applies to 316, exactly the same. 316 and 316L, the L is a lower carbon version of 316.
That's correct.
Going back to 304, can 304, given what you said about chlorides and not liking the 300 series, can 304 ever be used at the coast?
If you use 304 at the coast, 304 on its own will not withstand the effects of the chloride environment at the coast, and you will get staining, but it's unlikely you would get catastrophic corrosion. It will stain, and people who generally build things out of stainless steel want nice shiny structures and plant and so on, and 304 will not maintain that. It will stain under marine conditions.
So which applications would most typically lend themselves to the use of stainless steels in heavy industrial projects? Would you use them primarily in mining, petrochemical? Why would you choose to use a stainless and not a conventional mild steel?
The general corrosion resistance of the material is way, way higher than that of conventional steel, of carbon steels. So you would use it in chemical processes where ordinary steel would corrode, and provided you haven't got this high chloride environment, you can build things out of stainless steel, which then will last significantly longer than their carbon steel counterparts. Often you also find that the basic or the underlying strength of the stainless steel is higher than carbon steel, and therefore you can make it out of thinner gauge material.
Which has cost savings.
Yeah.
And associated with that, obviously you wouldn't want to use a stainless steel in any application where it's not going to be exposed to air to keep that nanometer layer of passive forming material on the surface.
Absolutely right. You have to use them in oxidizing environments or aerated environments. If you expose stainless steels 304 more so than 316 because it is less resistant to pitting, if you expose those in situations where they are starved of oxygen, they do not perform particularly well.
Well, thank you. I think you've answered all of the questions that have come in. So thank you, Neil. I think that was really interesting. And it's always a wonderful opportunity to glean more information and understand a little bit more. So thank you for spending this time with us. And please don't forget to take advantage of our current launch special of our virtual CP101 course. You need to log in and pay before the end of April in order to validate the launch price special. So with that, I just want to say thank you very much again for joining us for Bite Size Corrosion. Thanks everyone, and enjoy the rest of the week.